Hello, let me present you solutions to selected homework problems part 1. Problem 1, so we're going to construct algebra Z4 and we'll show that it's not a field. So Z4 consists of 4 elements, 4 integers, and then we have 2 operations, the summation modulo 4 and multiplications modulo 4. Okay, that is defined, just I'm recording you as usual. So the best way to define these two operations is to use a table. Then, so we need to provide the result of this operation for each possible pair. Okay, first let's construct the table for the addition. Okay, so we have again four elements, so we have 16 possible pairs, and clearly if you add 0 to any number we obtain the same number, and clearly the operation is commutative, so as a result in table we obtain a symmetric table. Okay, so then now 1 plus 1 is 2, okay, 1 plus 2 is 3, 1 plus 3 is 4, modulo 4 gives us 0, okay, and then I just need to copy. Now 2 plus 2, 4, modulo 4 gives us 0, okay, then 2 plus 3 is 5, modulo 4 gives us 1, and finally 3 plus 3 is 6, modulo 4 gives us 2. Okay, so now the next one, multiplication. So this we have the same story. We need to define that operation using the table. Okay, so again, we're just taking the product, and then we need to find the remainder upon division the product by 4. So as usual, if you multiply 0 by something else, you obtain 0. Okay, so in the first column, the first row, we have zeros. If you multiply 1 by something else, you obtain the same number. Okay, so now 2 times 2 gives us 4, modulo 4 gives us 0. Okay, 3 times 2 is 6, so it's 2, and finally 3 times 3 is 9, so it's 1. Okay, just explain this. So 3 times 3, okay, modulo 4 equals 9 modulo 4 equals 1. Okay, so now I'd like to recall you that one of the field axioms is the following: every number has the multiplicative inverse. So for every a, say from Z4, we can find an element so that a times b equals 1. And now if you look at the second table, we see that for element 2 we have no multiplicative inverse. So if a is 2, then actually there is no element b from Z4, so that the product is 1. Okay, so therefore 2 doesn't have a multiplicative inverse, so therefore it's not a field. Okay, so let me consider the next problem. So for given set S, we are asked to find an upper bound, a lower bound, and the least upper bound and the greatest lower bound. Okay, so first let's discuss the properties of this set. So set S is a countable set and is formed by ratio of integers. So every element of this set has the following form: it's n divided by n plus 1, where n is the natural number. Okay. First, we can observe that actually this sequence is strictly increasing. Okay. So how we can prove that? Okay, I will start first with the common inequality with 0 less than 1. Okay, then I multiply, then I add n squared plus 2n to both parts. Okay, and then I will obtain here the product n times n plus 2 less than n plus 1 squared. And now I can divide by n plus 2 and n plus 1 to obtain n over n plus 1 is less than n plus 1 divided by n plus 2. So clearly, in this sequence S, every new element is greater than its predecessor. So therefore, the sequence is strictly increasing. Okay. Also, it's clear that sequence is bounded from above. Okay. So for every natural number, n divided by n plus 1 is less than 1. Okay. Why? Because it's equivalent to inequality n less than n plus 1. Okay. And also we have that since strictly increasing, every element is not less than the very first one, which is 1/2. So 1/2 will be actually the least element. Okay. So now, how we can find an upper bound? Okay. So we can use, for example, this inequality to find the upper bound, and then x equal 1 will be an upper bound. A lower bound can be taken any number that is, because all elements are positive, we can take, for example, 0 or any negative element as a sample lower bound. Okay. Now my claim is that the least upper bound, so which is just supremum of S, is 1. Okay. So clearly every element of this sequence is less than 1. So 1 will be an upper bound. By y, it's the least upper bound. So to prove that, we need to prove that for every epsilon greater than 0, we can find a natural number so that this element n over n plus 1 will be larger than 1 minus epsilon. Okay. So in other words, we cannot find any other upper bound that will be less than 1. Okay. So 1 minus s cannot be 1 minus epsilon cannot be an upper bound. Okay, indeed it's so if you just do usual manipulations, we can obtain that if n is taken to be the ceiling of the ratio 1 over epsilon plus 1, okay, then in this case this inequality will be satisfied. Okay. So therefore, 1 is the supremum of S, or the least upper bound. Now the infimum of S is clearly 1/2. Okay, why? Because sequence is strictly increasing, and 1/2 is actually the very first element. So every other element will be not less than 1/2. So the next problem is about the infinite hotel. So we have an infinite number of rooms, numbered 1, 2, 3, and so on. And actually all the rooms are full. And then we have a countably infinite number of people, new guests, that all show up at the same time and ask for their own rooms. And the desk manager is going to accommodate all of them. Okay? So how is going to do that? How is she going to do that? So we have to move actually all old guests into new rooms. So the idea is that we move the person, okay, from room number n, okay, so n again is a natural number, to room number 2n. Okay, so here's the table. So how it works? So we have old guest in room number 1. It will go to the new room number 2. So the guest from room 2 will go to room 4. From 3 goes to 6, and so on. Okay. So now what will happen, all rooms with even numbers will be occupied, and all rooms with odd numbers will be free, and then we can put all new guests into this room. Okay. So we have to enumerate all the guests. So, and the new guest, okay, number m, okay, actually goes to room number 2m minus 1. Okay, so here's the table. New guest, room, guest 1 goes to room 1, guest 2 goes to room 3, guest 3 goes to room 5, and so on. So in this case, new guests will occupy the rooms with odd numbers. And that's conclude the solution. Alright, let me begin the last problem for this presentation. So for set S that consists of these points, we are going to find all the interior, exterior, and boundary points, all limit points, and also decide whether S is an open set or S is a closed set. So let's observe that S is a countable set, and S consists of the points of the following form: 1 divided by n, where n is a natural number. And clearly, all points of S are isolated. So to prove that, we're going to construct an interval that surrounds each point so that intersection of such an interval with S is has only one element, that point itself. So for example, for 1 we take the following interval: 0.9, 1.1, intersection with S gives us 1. Okay, and then for every natural n greater than or equal to 2, we have the following interval: 1 divided by n plus 1, 1 divided n minus 1, intersection f's again gives us only 1 point, 1 over n. So all the points are isolated. Okay, so therefore these points cannot be accumulation points. Okay, so let's first answer part B. So this derived set S prime, okay, doesn't have any points of S, but it has only one point, 0. Why so? To prove that, we can observe that this sequence 1 over n actually converges monotonically to 0 as n approaches infinity. So 0 will be the only limit point. So to prove that, by definition, we need to show that for every delta greater than 0, we can find n so that this point 1 over n contains in the interval minus delta plus delta. Okay, so since 1 over n is positive, we just need to solve this inequality. And then again we have solution. For example, n is equal to the integer part of 1 over delta plus 1. Okay. Alright, so now we can now answer part A. So since all the points of S are isolated, neither of them is an interior point. Okay, so the interior of S is actually empty. Okay, what about the exterior point? So exterior of S is defined as actually as the interior of the complement of S. Okay, and clearly it will contain some points of the complement, but it will contain one point. Clearly it won't contain 0, because again, if you take 0, then in any neighborhood of 0 you can find a point from S. Okay, for it doesn't matter how small is that interval. Okay, so therefore 0 cannot be an exterior point, it's a boundary point. So the exterior point of S contains all elements of the complement of S except 0. And now the boundary points are actually all the points of S and also 0. Again, why 0 is there? Because again, if you take a neighborhood, delta neighborhood of 0, you can always find a point from S that lies in that neighborhood. Okay, so for every delta, you can find a point from S so that we have 0 less over 1 over n less delta. Okay, but also we have a point from the complement of S. Okay, so let's conclude and let's answer part C. So clearly S is not open, since the interior of S is an empty set and it's not equal to S, therefore S is not open. Okay, and also S is not closed. Why? Because again, we know that S is closed, okay, if and only if S equals its closure, which as we know equals the union of S and the derived set. But since 0 is the only conversion point and that point is not in S, right, S cannot be closed set, so S is not closed. And that's it.